Alright, and continuing our study in Chapter 14, Section 2 actually talks about prisms. So this is actually our first 3D figure. And a nice complete definition of a prism is that a prism is a closed three-dimensional figure with two congruent and parallel boundary polygons. And then all the other boundary polygons are parallelograms. So here in this example, these two are examples. The the two congruent and parallel faces are rectangles, and then all the other sides happen to be rectangles as well. Not always the case. In the event that we do get rectangles for the other sides, this is actually called a right prism. And then similar thing here. The boundary polygons that are congruent and parallel are triangles. And now, from our earlier studies in geometry, we may already know most of these figures. A sphere is this first figure. We don't have any polygons here. Okay, a pyramid. We have a polygon as all sides. We have polygons as all sides, but we don't have two congruent and parallel polygons. Cylinder here, we have two congruent figures. Those figures are not polygons though, so circles, again, we can't identify those to be polygons. And then this last one is called an icosahedron or isocahedron, depending on how you want to pronounce it. All the figures are polygons, they're all congruent, but we don't necessarily have parallel sides. Okay, now continuing this, we're going to just kind of walk through some basic vocab, and just so we're on the same page. So the boundary polygons of a prism we call faces. So all these sides are faces. Okay, the two faces that are congruent and parallel of the prism we typically call the bases, and we name the prism after the base. So, for example, in this one we have the two congruent and parallel polygons being pentagons, the top and the bottom, and so those are the bases, and we would call this a pentagonal prism. Similarly, with this one, we would call this a hexagonal prism. Okay, and then the other sides that are not the base, we more commonly call those the sides. Okay, and as I mentioned before, if we have the sides all being rectangles, we actually call those right prisms, and then the other ones where we actually have parallelograms of sides, we call oblique prisms, which is an example of this one because we don't have 90-degree angles. Now, in the event that we actually have a figure that is completely composed of parallelograms, and yes, there is a typo here, you can fix it in your own slides. If a figure has all parallelograms as its faces, we actually call that parallelepiped. Okay. And then some more kind of background information on prisms is we have two types of area. We have lateral area and surface area. Now, lateral area refers to just the area of the sides. So if we sum all the areas of the sides, that will give us the lateral areas. So this does exclude the bases. Okay, so we don't talk about, at least in this case where we have this hexagonal prism, the lateral area would be the sum of the areas of the six sides, the six parallelograms, or in this case rectangles, that form the sides. Now, surface area, it includes the lateral area, but it's also the sum of the areas of the bases. Okay. Now, generally in your book does exactly the opposite of this. I think the best skill is actually to not remember specific formulas for surface area or lateral area for prisms, at least. Okay, other ones, when we talk about pyramids and cones and all that stuff, it will actually be more beneficial to remember formulas in that case, but I think a better skill is to really try to utilize the geometry that you already know each time to try and to determine the surface area and lateral area for each of these. Okay, but your book, I believe, lists the lateral area and surface area for a rectangular prism, right rectangular prism, and a cube. And the other number that we can typically compute with these three-dimensional solids is volume. And so this is by definition just the amount of matter an object contains. So now this is where some of the new stuff may come into play. So mathematically, when we compute the volume, what we actually do is we compute infinitely many cross sections that are parallel to the bases, and we start at the bottom base and continue and move that sheet up through. So if I were to just consider, I'll make a little sketch here. Okay, so I make a little sketch here. Here's my plane. And a cross section really is just I move a plane through a figure and see what results. Okay, so now I take this plane and okay, so here's my plane, and what I need to do is I need to move that through my prism. Okay, so right here when I move this through, I need to look at the shape. And so the shape that I would get, and this is not going to be perfect by any means, but it would look something like this. Okay, this is a kind of a bad drawing, but this would be that hexagon. This would be the same hexagon as the bases. So what I would need to do is I would compute the area of this hexagon, okay? And then I'm going to move the prism a little bit. And then I move it through the prism, up and down again from the bottom of this prism to the top of the prism. And I would have to each time I move it a little bit. So I compute that area here, I move it a little bit, compute that area, move it a little bit, compute that area, move it a little bit, compute that area, and I would add up all those areas, and that actually gives me the volume. So that's where our formula for the volume actually comes from, where we have to do the area of the base. Okay, so I'm going to say equals area of base. Okay, that's big B. And then times height. So I'd have to take that and multiply it by, again, I'd add it however many times, however high my figure is. So that is where the volume formula comes into play. The last thing, and this one might be new, but this is called a space diagonal. So it's a diagonal that actually moves through space. It's not that it'll lie on one plane, but it's not on any plane that is used to construct the prism of interest. So what this is that it is the diagonal extending through the prism from a vertex of one base to a non-planar vertex on the other base. So if I identify two vertices, so this one in the upper right and this one in the lower back left, the space diagonal would be the line, and maybe I'll just draw it solid here, that extends again through the prism from one vertex to another. Okay, and in the case of a right rectangular prism, we can actually show, and this can be done using triangles. You can use triangles, and we'll actually do that in a problem. But the space diagonal's length is actually given by the square root of the sum of the squares of the dimensions. So the square root of length squared times plus the square root of width squared plus the square root of height squared.